Okay, let me give you a couple of examples. So example one is example of a ladder that is slipping. This is a ladder that is essentially sliding or slipping um, along these floors. So let's say slipping like this. So this is point A over here. This is the point B. Those are the endpoints of this ladder. So A is coming down, point A is coming down, point B is moving towards the right. And we want to understand what are the relationships between velocity and acceleration of point A and B. Okay, so we'll start with the reference frame. That's our number one thing we do. So let's say we attach our reference frame over here. That's positive x direction, and that's your positive y direction. So position of A is, let's say, xb, and position of position of B is xb, and position of A is given by ya. Okay. So what are the constraints over here? Well, we know that this is a solid ladder. It's a rigid body, which means that this length is not going to change as A and B move, which means that when B moves towards the right, A is coming down by a certain amount, right? Okay, so let's say this angle is theta. So what we can write is, we can say that if length of this ladder is L, then we can say XB is equal to L times sine theta, and YA is equal to L times cosine theta, where L is actually a constant. So if I differentiate this once, what do I get? I get x dot b equal to, L is a constant, so it remains outside, cosine theta times theta dot. Notice that we are taking derivative with respect to time, while on the right hand side we have function of theta, so I had to introduce a change of variable. So this was essentially d over d theta times d theta over dt. So let me do that actually, so for once. So d over dt of L sine theta, L comes outside, so this is d over dt of sine theta, and now I introduce a change of variable, and I get d theta over dt here. So I get this is equal to cosine theta, so L cosine theta times theta dot. Okay, if I differentiate it once more, I get x double dot b equal to L. This would be minus sine theta times theta dot. So we have one more theta dot, so that the theta dot square plus cosine theta theta double dot, and that is x double dot b, right? Similarly, we can differentiate ya also. So let's do that. So y dot a would be equal to minus L sine theta times theta dot, and y double dot a would be equal to minus L, and this would be cosine theta theta dot square plus sine theta theta double dot. So what is this expression? This is nothing but velocity of B, and this is nothing but acceleration of B. This is acceleration of A, and that's velocity of A. Okay, so of course, to determine all of these quantities, you have to know some of the things. So let's say we know x as a function of xb as a function of time. If we know xb as a function of time, then we know x dot b, that gives us x dot b, and from that we can compute theta dot, right from over here. So this is x dot b. So from this we can compute what theta dot would be, and then we can differentiate it once more, and we will have x double dot b. And from that, now from the second relationship, let's call it 1, and this is 2, this is 3, and that's 4. So from this now we can get theta double dot. Once we have theta dot and theta double dot, we can substitute them in 3 and 4, and we can get the velocity of A as well as acceleration of A. So this is an example where we essentially looked at the constraints of a ladder, and we related the velocity and acceleration of 2 points on that ladder. Let's look at another example. So let's say I have a pulley, okay, and I have a load attached to it. Let's say we'll call it A, and then we have another load attached over here, and which we'll call B, okay. So in this case, let's say this is a very simple pulley, right? We want to understand the relationship between velocity and acceleration of A and B. In this case, you don't even have to do much analysis, because by whatever amount B comes down, let's say B was coming down because it was heavier than A would go up by the same amount, right? Which means that their velocity and the acceleration would be identical magnitude-wise, but their directions would be different, right? And this part is fairly easy to understand. So let's look at a slightly more involved scenario. So let's say we have pulley like this, then we have a block attached to it, we'll call it A. Then this goes up and there is another pulley and that is attached to the ceiling. And then we have another block that comes down and we'll call it B. Okay, so now we have a double pulley arrangement over here. And in fact, this is called a block and tackle system. So you may have seen this in your status class as well, where you were trying to reduce the effort at one end to pull a load up, right? And depending on how many pulleys you had, you would be able to get more mechanical advantage at the cost of pulling the rope more, right? Your total work done would always be same, but at least you would reduce on the effort. I mean, that's the whole principle behind the cranes. If you've ever seen a crane out there during the construction zone, and if you look carefully, I know it's not easy because usually the pulleys are right on top and you can't see them very well. There are multiple of those stacked out right on top of each other, and the rope essentially goes over multiple pulleys, and that's all because you want to reduce the load on the motor, which is going to pull the cable, which in turn is going to pull the load up. So let's come back to this simple example with two blocks A and B, and we want to understand what is the relationship between the motion of A and the B. So whenever you're given a problem where you have to compute the relationship between the motions of two or three particles, you have to start by assuming a coordinate system and showing the position variables. Okay, so we would attach our we would attach our reference frame to right to the ceiling, and we will indicate the position variables positive in the downward direction. So YA and YB, and notice that we don't need more than two position variables over here because we have only two particles, and we only need one direction because A and B are going to be moving up and down. So we really don't need a full-fledged coordinate system showing I hat and J hat and K hat because this is all translational motion along vertical direction. So downward is positive direction. So let's keep that in mind. So this is positive. So this is, let me say this is positive y direction. And remember, you can choose any direction to be positive direction. It can be downward, it could be upward, it could be an angle, and so on. So let's try to understand what is the relative motion between A and B. Again, in this case also, you could probably see how motion of A and B would be related. So let's say I move A up by a certain amount, right? Let's say I move it up by, I don't know, maybe 1 inches. So if I move A up by 1 inches, what happens is this pulley that you see over here, right, moves up by 1 inches as well, right? So it moves to a new position which is 1 inches above. So going from here to here, it has gone up by 1 inch, right, as it moves up by 1 inch, which means that on the both sides of the pulley, on this side as well as this side, 1 inch each would be freed up, right? And of course, you assume that there is no slack in the system. So this 1 inch and 1 inch together, which will be 2 inches, will wrap around this pulley right over here, and it will be released on the other side. So which means that B would actually come down by 2 inches. So if this went up by 1 inch, the B would come down by 2 inches. So in this case, you could have kind of seen what was going on by just examination, right? But this is not the method that I would advocate for you to use, where you have to use your intuition to solve the problems. In fact, this is one of the things that's very different about engineering dynamics from from physics class, is that you rely less and less on your intuition to solve the problem. You rely on the process, on the procedure, on the techniques to solve the problem, all the problems in the same way, instead of looking for one approach to solve one problem, another approach to solve another problem. Okay, so let's say we want to solve this problem in a systematic way. So we'll go back to where we were. So we're just going to undo all this so that we don't have all these red pens. Okay, this is where we were. Okay, one more time. Okay, so let me just erase this. I guess it has limited memory. All right. So what is the constraint over here? The only constraint over here is that the length of this cable remains fixed. So this cable that is running all over these pulleys connecting the blocks remains fixed. This part of the cable is of course a fixed length. This part of the cable is of course of the fixed length, right? So the only constraint is that there is no slack and the length of the cable is going to be fixed. So it is not extensible. It doesn't stretch, it doesn't contract. We assume that. It's not like an elastic rubber band. So if the length of this is constant, so we will start with that by saying that the length L of the cable is constant. So if I can express the length of this cable L in terms of these position variables, then maybe I will have a geometric relationship that would describe the constraint between the motion of A and B, right? So let's do that. So what we will do is we will identify the different sections of this cable and ask the question as to what their lengths are, right, in terms of these position variables. So going from here to here, so let me call this as, I don't know, we will call it L1. So what is this L1? Well, L1 is equal to the position variable YA minus this length, right? So let's call this length, I don't know, we'll call it F1 because this is actually a fixed length, it doesn't change. So L1 is equal to YA minus F1, where F1 is fixed. Now let's talk about this part of the cable right over here. Okay, let me pick my blue color. This part of the cable. What is this? So let's say this radius is R and this is a semicircular. Then this part, we'll call it L2, which is the curve length, is pi times R, right? Which is also fixed because the radius of the pulley is not going to change. Yeah? And we'll assume that it's always a semicircular, or whatever the contact length is, it remains same. Now let's get to over here. So from here to here, what is this length? This length, we'll call it L3, is equal to, again, YA minus F1 minus this length, which we'll call F2, which is also fixed, right? So that's L3. Finally, we have, this, okay, we have this as well. So we'll assume that this is same as L2 and we'll call it L4, okay? That's your wrap length. And then finally, we'll have L5 going from here to here, and L5 is equal to YB. Remember, our goal is to write everything in terms of position variable. So YB minus F2. And the total length L of the cable is L1 plus L2 plus L3 plus L4 plus L5, which is constant. All right, so let's substitute for each of these L1, L2, L3 up to L5 in here, and we get YA minus F1 plus pi R plus YA minus F1 minus F2 plus L4, which is pi R, finally L5, which is YB minus F2, and that is a constant. Okay, so let's collect all the position variables. So we get 2YA plus YB minus F1 plus pi R. So I'm going to just select all these over here. So that's actually 2 pi R minus and 2F1 minus F2 and then 2F2 actually, so minus 2F2 equals to constant. This is all constant over here, right? So this constant can be taken on the other side, right? And the right hand side would still be a constant. So we will be left with 2YA plus YB equal to some constant. Okay, it could be a different constant, but it doesn't matter. This is at some constant length. If it is 5 inches, it's always 5 inches. Now we can differentiate it, and we get 2 velocity of A plus velocity of B equal to 0. We differentiate once more, and we get 2 acceleration of A plus acceleration of B equal to 0. And that's the relative motion analysis that we wanted to perform on this particular block and tackle system. Now going forward, we won't really be writing individual lengths like this, okay? We will look at the lengths of the cables and we'll say, okay, can we express them in terms of the given position variables? And we will continue to neglect the constants. We will neglect the area that is wrapped around the pulleys and things that are fixed in length, and we will say they're just constant. So our focus will be just on the position variables. So now, knowing these two relationships, what can we do with them? Well, we can answer questions like these. If the velocity of A is known, we can compute the velocity of B. So velocity of B would be minus 2VA. And that is same as what we saw before when we tried to figure this out sort of intuitively, right? By making the A move up and then seeing by how much distance B comes down, right? You could also be given the velocity of A or velocity of B in an indirect way, like, you could be told that the particle A moves up or moves down by a certain distance under constant acceleration in a certain amount of time. Now you have to find by how much B would move down or what velocity would be and what its acceleration would be.